Thanks for viewing this video. My name is Junyao. I will be presenting randomized communication complexity of randomized auctions. This is joint work with my advisor, Aviad Rubinstein. So I want to start by introducing the problem setup. So in multi-item Bayesian auctions, we have a seller and a single buyer. The seller has n items, for example, 2 items, an apple and a banana. The buyer has a private valuation V that maps from a subset of the items to a real value, and the valuation function is drawn from some prior distribution D. I want to make 2 notes. First, the valuation class can be additive, unit demand, or any class of combinatorial valuations. And the seller only knows the prior distribution D, but not the private valuation. So in this problem, the buyer wants to maximize his utility, namely the value he gets minus the payment. And the seller wants to maximize the revenue, namely the buyer's payment. So they want to talk through some auction protocol. So they talk to each other after some rounds, and finally they make a deal with each other. For example, the buyer gets the apple and pay $1. The goal of auction design is to design an auction protocol that maximizes the seller's revenue using minimum possible communication. In this slide, I just want to introduce some examples of revenue maximizing auctions. In case of single item, regardless of the prior distribution, the celebrated result by Meyerson shows that selling the item at a fixed price is optimal. So in this case, there are just 2 possible outcomes. Either the buyer gets the apple for some price, or he gets nothing and pays nothing. This auction can obviously be implemented using 1 bit, just to let the buyer indicate whether he wants to buy or not. In case of 2 items, and suppose the buyer's valuation is additive over these 2 items. If the prior distribution is uniform over 0, 1, and 2 for apple's value, and similarly for banana's value, and their IID, it turns out for this prior distribution, the optimal auction is just let the buyer buy any single item for $2, or buy both for $3, or buy nothing. And this can be done using 2 bits, just to let the buyer indicate which option he likes the most. Things get much more interesting when we have a beta distribution for the apple and we have another beta distribution for banana. It was previously shown for this prior distribution, any deterministic revenue maximizing protocol needs infinite communication. In contrast, our paper studies randomized auctions, and the randomized protocol in our paper only uses less than 2 bits in expectation. Before I state our results, I just want to go through some formalities. So unless specified otherwise, we want our randomized auctions to be incentive compatible. Namely, buyer only chooses strategy that maximizes his expected utility, which is expected value minus expected payment. We also want the protocol to be individual rationale. Namely, buyer only chooses strategy such that his expected value is larger than expected payment. We also want the auction to be revenue maximizing for every prior distribution. Namely, it should maximize buyer's expected payment. Here, the expectation is over prior distribution and the randomness of the protocol. Finally, we want the auction to be communication efficient in expectation. Here, the expectation is only over the randomness of auction protocol, but not over the prior distribution. Now I want to tell you our main results. We provide randomized auction protocols for different valuation classes over n items that achieve exactly optimal revenue in expectation. And the auction protocol uses nearly linear bits of communication for additive and unit demand valuations, and exponential bits of communication for general combinatorial valuations. The closest previous work is a deterministic protocol that achieves nearly optimal revenue over independent items, namely, the prior distribution has to be a product distribution. The communication complexity of this protocol is n log n. However, this result is not comparable to ours because it only achieves nearly optimal revenue, and it assumes the prior distribution is a product distribution. Moreover, we provide matching lower bounds for our efficient protocols. Specifically, we show that to even achieve constant fraction of optimal revenue, we need roughly these amounts of bits of communication. I just want to highlight that randomized communication complexity lower bound for auctions is quite rare. In many cases, we just get started to understand deterministic lower bounds. Additionally, we give a super efficient protocol for unit demand valuation, which achieves nearly optimal revenue in expectation, and only uses polylog many bits of communication in expectation. On the other hand, as a corollary of our low bound results, we show that in our hard instances, the buyer's valuation has constant precision, and there exists a randomized protocol for this instance such that there is an exponential separation between the communication complexity of its approximately Bayesian incentive compatible implementation and that of its non-incentive compatible implementation, where the buyer is simply fully cooperative. And with a little bit more work, we use this corollary to resolve an open problem by Fadel and Segal. In the rest of the talk, I'll spend most time showcasing our efficient protocol for additive valuation. After that, I'll give you a very high-level sketch of our lower bound proof. Now I want to showcase our efficient protocol for additive valuation, so it achieves exactly optimal revenue using n log n bits. So actually we show a stronger result. We show we can actually implement any protocol, including any optimal protocol, using n log n bits. Specifically, we represent any protocol as a menu of lotteries. Then we let the buyer commit to a lottery on the menu. Then essentially we just design efficient randomized protocol to run the lottery without even fully revealing the lottery. So first I want to show you how to represent an auction protocol as a menu of lotteries. So given any randomized auction protocol, a strategy of the buyer can result in a distribution of output. The output is simply the allocated set of items to the buyer and the payment to the seller. So we can think of the distribution of output as a lottery. A lottery is just the distribution of allocated set and the expected payment. So the buyer's utility actually only depends on the lottery. For example, here is a lottery where the buyer gets every subset with a quarter probability, and he has to pay expected payment 1. Therefore, every strategy of the buyer is essentially equivalent to a lottery. Moreover, given a randomized protocol, the buyer has the freedom to choose any strategy. because we have shown each strategy is essentially a lottery. The protocol can be simply viewed as a menu of lotteries which the buyer can choose from. For example, here is a menu where every line is a lottery. Furthermore, for additive valuation, because of linearity of expectation, we can show that the buyer's expected value is linear in probability of getting each item. Therefore, a lottery is, without loss of generality, represented by a distribution over items instead of sets, and the expected payment. So here is our new menu, where every line we have expected payment and the probability of getting each item. Without loss of generality, we can assume the expected payment is in the interval between 0 and 1 in every lottery. This is because for any payment U, we can normalize it by the upper bound of buyer's valuation, which we denote by capital U. This is because by individual rationality, the buyer can never pay higher than this value. And we can let the buyer pay this upper bound with probability Q, defined as U divided by capital U. Now I want to talk about our efficient protocol. Given any menu, we first let the buyer commit to a lottery on the menu. Potentially, the lottery requires infinite bits to represent. A naive protocol to run the lottery would be just letting the buyer send the lottery to the seller, and then let the seller sample a random number between 0 and 1. If the random number is smaller than the probability of getting the apple, then the seller would just allocate the apple to the buyer. If otherwise, the seller does not allocate the apple to the buyer. Also, the seller makes similar decisions for the other items. For the payment, if the random number is smaller or equal to the expected payment on the lottery, the seller would ask the buyer to pay the upper bound of the valuation. If otherwise, the buyer does not need to pay anything. An issue with this naive protocol is that because the lottery might need infinite bits to represent, at the first step of the naive protocol, it also requires infinite communication. Our solution is, instead of sending the entire lottery at one step, we send it sequentially. That is, in each round, we let the buyer send 1 bit for every number in the lottery, starting from the most significant bit. Then the seller samples 1 bit for the random number each round, also starting from the most significant bit. Then essentially, seller could just make these comparisons on the truncated version of these numbers. So the decision rule is the same as here, except if the seller observes an equality, he would not make a decision at this round. He would defer the decision for that item or the payment to the later rounds. By very basic probabilistic argument, we can show that with high probability, the random number will differ with every partial number of the lottery after logarithmic number of rounds. Therefore, the protocol is efficient. Let me give you a simple example. Suppose there are just 2 items, and the menu is the following. Suppose the buyer commits to the lottery in the first line of the menu, and the seller maintains a random number that initially is 0. In the first round of the protocol, the buyer sends the first bits of the numbers in the lottery, which are 1, 0, and 1. Then the seller draws a random bit as the first bit of the random number. say it's 1. And the seller compares the current random number with the partial numbers of the lottery. Because the current random number is larger than the partial number for the probability of getting the banana, the seller decides to not allocate the banana to the buyer. And because the other comparisons are all equalities, the seller will not make any further decisions. Similarly, in the second round, the buyer sends the second bits of the numbers in the lottery, which are 1, 1, and 0. And the seller draws a random bit as the second bit of the random number, say it's 0. Then the seller compares the new random number with the partial numbers of the lottery. He observes the current random number is smaller than the partial number of the probability of getting the apple. Therefore, he decides to allocate the apple to the buyer. The comparison with the partial number for the expected payment is still equal, so it's not decided at this round. Finally, in the third round, buyer sends the third bits of the numbers in the lottery, which are 0, 0, and 1. And then the seller draws a random bit as the third random bit of the random number, which is 0 in this case. Then the seller compares the current random number with the partial numbers of the lottery. He observes the current random number is smaller than the expected payment. Therefore, he asks the buyer to pay the upper bound of the valuation, and the protocol is finished. For the reference, I give you the full protocol in this slide. So I will not go over it again because it's basically the same as the example I just did. So if you are interested, feel free to pause the video and read it by yourself. Now I want to switch to the lower bound results. Recall that we show for unit demand valuation over n items, it requires linear number of bits of communication in expectation to achieve any constant fraction of optimal revenue. I'll give you a brief proof sketch later, but before that, I just want to highlight standard techniques for proving communication complexity lower bound, such as reduction to set disjointness, does not work here, because such a reduction would also work for non-incentive compatible protocols. However, in the paper, we show a logarithmic communication non-incentive compatible protocol for unit demand valuation. Therefore, such a reduction can never prove our lower bound. To get around this, our proof employs a characterization of incentive-compatible protocols as protocol trees. In the last slide, I'll give you a very high-level proof sketch of our lower bound. The first step of the proof is to construct a family of 2 to the omega n prior distributions of unit demand valuations over n items. And then, as second step, we show there is a randomized protocol that achieves full revenue for every prior distribution in the family. Therefore, the optimal revenue is full revenue. In the third step, we represent any randomized protocol for prior distribution by a protocol tree. So this is a characterization I just mentioned. We show the randomized communication complexity is basically the depth of the protocol tree. Then we prove one protocol tree cannot simultaneously achieve any constant fraction of full revenue for super constant many prior distributions in the family. By simple counting argument, there are 2 to the little o of n depth little o of n protocol trees in total. Each of them achieves constant fraction of full revenue only for constant many prior distributions. Therefore, in total, they can only solve 2 to the little O of n prior distributions, but there are 2 to the omega n prior distributions in total in our family. Therefore, all the randomized protocols with little O of n communication in expectation cannot achieve constant fraction of optimal revenue for most prior distributions in our family. To conclude, in this paper, we show communication efficient and revenue maximizing randomized protocols for multi-item Bayesian auctions with different valuation classes. We also have nearly matching lower bounds. A corollary of these lower bounds resolves an open problem from Fadel and Skull. Finally, I want to plug a little advertisement. There is another talk in this session that answers a different open problem from Fadel and Skull. Thanks for viewing.